Hi, today I'll be talking about two papers on a connection between the set cover conjecture and the asymptotic rank conjecture. The first paper is the asymptotic rank conjecture, and the set cover conjecture are not both true. This is by Andreas Björklund and Petri Koski. The second paper is my paper, A Stronger Connection Between the Asymptotic Rank Conjecture and the Set Cover Conjecture. So this talk is about the possibility of using algebraic methods which have been studied extensively in the context of fast matrix multiplication to refute a conjecture in the area of fine-grained complexity. So to set the stage, recall that in 1969, Volcker-Strawson showed that two n by n matrices can be multiplied using only n to the 2.81 many arithmetic operations, which showed that the naive n cubed time algorithm for matrix multiplication is not optimal. Since then, there's been a lot of work on determining the smallest real number omega for which n by n matrix multiplication can be done using n to the omega plus little o of 1 many arithmetic operations, with the ultimate goal of proving the popular conjecture that omega equals 2. Now, the fact that matrix multiplication can be done in subcubic time has many algorithmic applications. So unsurprisingly, it turns out that omega determines the complexity of many of the basic problems in linear algebra, like computing the determinant, computing inverses, computing QR decompositions, and more. But it's also the basis of some of the fastest algorithms that we know of for a handful of combinatorial problems, such as detecting triangles and graphs. Now, the core idea behind Strawson's algorithm and all subsequent improvements to omega is to give an upper bound on the rank of the matrix multiplication tensor. So I'll explain soon what these words mean. And one theme of this talk is to ask if this framework can be applied to other tensors to give faster algorithms for combinatorial problems for which fast matrix multiplication is not known to be useful. So the rest of the talk will be organized as follows. Next, I'll introduce the set cover conjecture. This is a fine-grained hardness conjecture for the set cover problem, which informally says that set cover on a universe of size n requires 2 to the n time. After that, I'll introduce the asymptotic rank conjecture of Strawson. And this is a certain generalization of the conjecture that omega equals 2. Very informally, it says that degree 3 polynomials with a certain recursive structure can be evaluated efficiently. After that, I'll state the result of Björklund, Koski, and myself. So Björklund and Koski show that these two conjectures cannot both be true, and then I gave a simpler proof of this fact with better quantitative bounds, and then I'll give you a sketch of my proof. Okay, so the algorithmic problem we're interested in is I'll call it the K set cover problem. So we're given a family F of K element subsets of an n element universe, and we're also given an integer t, and we're trying to decide if there exist t sets in the family that cover the universe. So this is classically known to be NP-hard when k is at least 3. So we don't expect a polynomial time algorithm, but we'll be interested in fine-grained hardness of this problem. It's been known since probably at least the 50s that this problem can be solved in time, some polynomial in n times the size of the set family times 2 to the n, just by some simple dynamic program. And the set cover conjecture states that for large enough k at least, this simple dynamic program is essentially the optimal algorithm. So more formally, it says that for any epsilon greater than 0, there exists some natural number k such that k set cover cannot be solved in time 2 minus epsilon to the n. This conjecture was proposed as it would imply fine-grained hardness results for a handful of problems for which we do not have fine-grained hardness results under the more popular strong exponential time hypothesis. And as a side note, there are no known implications between Seth and the set cover conjecture. So the second part of the story concerns tensors and tensor rank. For our purposes, a tensor is just a degree 3 polynomial in 3 sets of variables, so x variables, y variables, and z variables, where every monomial is a product of one variable from each of these 3 sets. So it's a set multilinear polynomial. It turns out that the field we work over is not important in this talk, so for simplicity, you might as well just imagine it's the rationals. Now, just as we can view bilinear forms as matrices, we can, of course, view 3 tensors as 3-dimensional arrays that are indexed by the 3 sets of variables, and where the entries in this 3D array just specify the coefficients of the monomials. Now, we say that a tensor has rank 1 if it factors as a product of linear forms, and then the rank of the tensor is just the minimum number of rank 1 tensors whose sum is equal to our tensor. So this notion of tensor rank is very old, and it's just a simple generalization of the definition of the rank of a matrix as the minimum sum of outer products. Okay, so to illustrate, one tensor that turns out to be interesting is what I will call the small Coppersmith-Winograd tensor. This is a 3x3x3 tensor, and you can describe it as follows. So if we think of it as a 3D array, then there will be a 1 in entry whenever the 3 indices are distinct, and otherwise this entry will be 0. And now it turns out that this tensor actually has rank at most 4, and this follows from this identity that I'm claiming. So if you expand everything, you'll see that I'm actually telling the truth. And I'm sure you won't do that. Now, another tensor of major interest is the 2x2 matrix multiplication tensor. This is just can be described as you sum over I, j, and k integers between 1 and 2, and you have a monomial xij times yjk times eki. So this is some 4x4x4 tensor. So Strawson's 1969 result is now usually interpreted as showing that the rank of this tensor is at most 7, versus which improves on the trivial upper bound of 8. Now, unfortunately, tensor rank is quite intractable, so it's hard to compute the rank of tensors, and it's a very mysterious quantity, so it's known that almost all n by n by n tensors have rank close to n squared. However, we don't know of any explicit families of tensors that have rank even at least 4 times n. So we'll be interested in the behavior of tensor rank under the Kronecker product operation, which I'll now describe. So given an n by n by n tensor T and an n prime by n prime by n prime tensor T prime, we define their Kronecker product to be the n prime by n prime by n prime tensor that is obtained by replacing every entry in T by a copy of T prime that has been scaled by that entry. So that's, in words, what this formula here says. And this is nothing complicated. It's just the most obvious way of generalizing the Kronecker product of matrices to 3-dimensional arrays. So, for instance, here's a picture of what taking the Kronecker product of the Coppersmith-Winograd tensor with itself looks like. Now, it's not hard to show that tensor rank is submultiplicative under this operation, and so we can therefore define the asymptotic rank of a tensor as the limit as r goes to infinity of the rank of the rth tensor power of Kronecker power of t to the power of 1 over r. So this is the parameter we'll be interested in today. And the motivation for studying this, of course, comes from matrix multiplication. So it turns out that omega is equal to the log of the asymptotic rank of the 2x2 matrix multiplication tensor. So if we, for instance, use the fact that the rank of 2x2 matrix multiplication is at most 7, this theorem tells us that omega is at most log base 2 of 7, which gives that first result. of Strawson's. Now, as another interesting example, we saw that the Coppersmith-Winograd tensor had rank at most 4, and therefore it has asymptotic rank at most 4. But Coppersmith and Winograd noted that if this tensor has asymptotic rank 3, then this actually implies that omega equals 2. So now, Strawson made a conjecture about asymptotic rank, which is very general. He essentially conjectured that the asymptotic rank of any n by n by n tensor is at most n. So this is a very general conjecture, which in particular implies that omega equals 2, because it implies that the rank of the 2 by 2 matrix multiplication tensor would be equal to 4, and so omega would be log base 2 of 4, which is 2. But for us, the important consequence, one important algorithmic consequence of this conjecture, if it's true, is that the polynomial, the tensor t to the r, can be evaluated in time n to the r times 1 plus little o of 1. So this is essentially the fastest algorithm you could hope for evaluating t to the r. And this is just because t to the r is a polynomial in like n to the r many variables. So this conjecture would imply extremely fast algorithms for evaluating certain degree 3 polynomials. Okay, so Bjorklund and Koski showed that if the asymptotic rank conjecture is true, then there's some slight exponential speedup over the dynamic programming algorithm for set cover. And it's interesting to note here that they don't actually use the full asymptotic rank conjecture. Instead, they only need that a particular 7 by 7 by 7 tensor has sufficiently low asymptotic rank. So I then showed that the runtime, the hypothetical runtime for set cover under the asymptotic rank conjecture, can be improved to 1.89 to the n. And this time I assume the asymptotic rank conjecture for a particular tensor that can be thought of as a generalization of this small Coppersmith-Winograd tensor. But amusingly, the tensor that gives this result is enormous. It has probably way more than like 10 to the 12 many variables. Okay, so I'm almost ready to sketch my proof. And the way that I got this result is by considering the following problem, which I'll call the balanced tripartitioning problem. So here we're given as input 3 families of subsets of an n-element universe, where the sets each have size n over 3. And we're trying to decide if there exists one set from each family, with these 3 sets covering or equivalently partitioning the universe. So the fastest known algorithm for this problem runs in time 2 to the n times a polynomial in n. This can be done using the fast Fourier transform, for example. But our strategy to show that the asymptotic rank conjecture implies the set cover conjecture is false will be the following. So first, we would want to say that if we can solve this balanced tripartitioning problem in time much faster than 2 to the n, then the set cover conjecture would be false. And this first step is just a pretty easy, pretty standard reduction. So I'll just talk about the second step, which is to show that if the asymptotic rank conjecture is true, then this balanced tripartitioning problem can be solved pretty quickly. So in time less than 1.89 to the n. So the way this will work is by assuming the asymptotic rank conjecture for the following family of tensors, which generalize the small Coppersmith-Winograd tensor and correspond to the balanced tripartitioning problem in a pretty obvious way. So we define T sub s to be the tensor indexed by subsets of a 3S size universe of size S, and we have one monomial for every partition of the universe into 3 balanced parts. Here are some pictures of these tensors T sub S for some small values of S. So when S is like 1, 2, and 3. Now note that when T equals 1, this is actually just the small Coppersmith-Winograd tensor. So one idea would be the following. If we were able to evaluate this polynomial T sub n over 3 quickly, then in time much less than 2 to the n, then we would be done. This is just because, well, we could just evaluate it at the indicator vector of the 3 set families, and that would actually count the number of balanced tripartitions. Now we don't quite do that, but we'll do something kind of similar. So for simplicity, let's first assume that n is equal to 3s times r. So now we call a subset A of the universe block good if the intersection of A with consecutive intervals of the universe of size 3s has size equal to s. Next, notice that by definition of the Kronecker product, if we take the rth power of T sub s, what we get is the sum of all monomials corresponding to tripartitions that involve 3 block good sets. Now, the basic idea is that, well, first, all of these monomials correspond to valid tripartitions, just a restricted kind of tripartition. And moreover, if S is large, then many of the tripartitions will show up. So our algorithm will just be the following. We repeatedly will choose a permutation on the n-element universe and define 3 no-set families, f1', f2', and f3', as the families obtained by permuting the universe and then only taking the permuted sets that happen to be block good. Then after that, we evaluate T sub s to the r at the indicator vectors of these 3 set families. And note that if this evaluation is non-zero, then, well, there is a tripartition on this permuted universe that only involves block good sets. And hence the inverse of this tripartition was a valid tripartition in the original input. And so we should return yes. On the other hand, if we've repeated this some number of times and we never returned yes, we return no. So by what we said, there will be no false positives. And furthermore, suppose that we have a yes instance, so there's some tripartition in the input. Then we will detect this, so this evaluation will be non-zero, exactly when the permutation sigma sends each of the 3 sets involved in this tripartition to block good sets. And we can calculate that this happens with probability at least 7 over s squared times r. So if we perform this test, this loop 1 over p many times, we will detect a tripartition if it exists with some constant probability. So the total runtime will essentially be the number of repetitions times the cost to evaluate this tensor. By what we said earlier, we can bound the cost of evaluating this tensor by the asymptotic rank of T sub s to the power of r times 1 plus the below of 1. Now, if the asymptotic rank conjecture holds, the asymptotic rank of T sub s is equal to 3s choose s, which is less than 6.75 to the s. So this gives us some hypothetical runtime bound under the asymptotic rank conjecture. And if we take s and n to be sufficiently large constants, this is at most 1.89 to the n, which proves the claim that the asymptotic rank conjecture gives a 1.89 to the n time algorithm for balanced tripartitioning. Okay, so in conclusion, we've shown that good asymptotic rank bounds on the tensor T sub s can potentially be used to refute the set cover conjecture. So what do we know about the rank of this tensor T sub s? So it can be shown that it's at most 8 to the s and it's at least 6.75 to the s. So if you go through this argument I just sketched in closer detail, you'll see that actually to break the set cover conjecture, you would only need to show that the rank, or the asymptotic rank of T sub s, is at most 2 over 9s times 8 to the s. And this would break the set cover conjecture. So you only need some slight improvement to this upper bound to break the set cover conjecture. And if this is not possible, then this is some breakthrough lower bound in arithmetic circuits. So in either case, there's something interesting. And of course, then the next question is if some of the tools used to bound the exponent of matrix multiplication can also be used to give good rank bounds on these tensors T sub s and refute the set cover conjecture. Thanks.